Hello and welcome to another video. Today we're going to be working on Count Beautiful Strings 2, the last problem from Weekly Contest 373 on Saturday. And this is the same problem as the second one, except the constraints are tougher now. So remember in the second one, we were able to get an n-squared solution, and here this is going to be significantly tougher. And I would say you're going to learn a lot from this one, and it's going to be basically like 3 or 4 medium problems in one. So for these hard problems, they're very hard to get unless you're like a competitive programmer, to be honest. So I would say if you can just follow a solution, understand every single part, and be able to replicate it, like if you were asked this question again, like 2 weeks later, can you code it up? And honestly, coding up the solution is also not super easy. So in the problem, it's a pretty basic description. You're given a string s and a positive integer k, and you have vowels and consonants, and that's the number of vowels and consonants in a string. String is beautiful if the number of vowels is the number of consonants, and vowels times consonants mod k equals 0. Return the number of non-empty beautiful substrings in string s. String is a contiguous sequence of characters in a string, and here are the vowels. So in the first example, there are 2. There is this right here. There are 2 vowels and 2 consonants. And in the second example, there are 2 as well. There are 2 vowels and 2 consonants. In the third example, for k equals 1, there are 3, and in the fourth example there are none. And here we have the constraint, so we need basically like an n log n or a linear time solution or something pretty good, where in the first one I think this was like 1,000, so an n-squared solution was doable, and that was pretty easy because we could literally just make every single string possible. So let's start out by figuring out that we really just care about the number of vowels and consonants, so it doesn't really matter what they are. Like A, B, B, A would give you the same answer as like A, C, C, A. Okay. So what I've done in the beginning is we're just gonna have a string with only A's and C's because it doesn't really matter which characters they are. We're basically grouping it into vowels and consonants. So here we have a string, 10 letters of A's and C's. Now we want a really easy way to figure out how many vowels and consonants there are. And it's still not as good as we'd want it. So the way to do this is we can actually, because there's only vowels and consonants, and we want an easy way to like sum it up, we're actually going to make our vowel, you can do this either way, we're going to make our vowel a 1, and we're going to make our consonant a -1. So if we rewrite this, so let's just copy this thing here, put it down here, and now let's change all of these to 1s and -1s. So we will have a 1, -1, -1, 1, -1, -1, 1, 1. And then if we add up a chunk, we can know if that's valid, right? So just to make sure I did this correctly, so we should have 5 consonants, yeah, and 5 vowels, yeah. Okay. So for example, for this chunk, for this like substring, this would not be the same vowels as consonants, but you could find some that are, right? For example, here, this one would work. And if we go to our original word, this does have the same. So now we need a fast way of actually getting this. And so for a fast way, we need a fast way of figuring out like what chunk has the same number of vowels and consonants. So essentially what we're asked is, given some region, can we figure out if this whole length is 0? So this is basically asked, like, given some chunk, can we figure out if the sum of this whole thing is 0? And there is a way to do this with prefix sums, right? Like we can basically just maintain a prefix sums array, and then that way, given 2 indices, we can figure out if the substring from between those 2 indices does indeed have an equal number of vowels and consonants in O of 1. So we're going to copy this one more time, and we're going to have a prefix sums this time. And we're going to do one little addition, and I'll explain it. We're going to need it down the road. But essentially what we're going to do is we're going to add one more location. And this is going to be 10. And what's going to happen here is 0 is actually going to represent the number of vowels and consonants in an empty string. And so vowels will be in a string of length 1, string of length 2, string of length 3, and so on, right? So let's do that, because we're going to need this for the next part. So what's going to happen is in an empty string, we will have 0 vowels and consonants, obviously. Now for a string of 1, it's going to be the previous one plus index 0. So these are the indices and these are the length of the string, actually, right? So a string of length 1 means it's going to contain this character at index 0. A string of length 2 means it's going to contain characters 0 and 1 and so on. So what we can do is we can just say, okay, now we can start adding these up. So this will be like 1, 1, then 2 will be both of these added, so it'll be 0. Then we add this one, so -1, add this one, 0, add this one, -1, -2, -3, -2, -1, 0. So this is a little confusing, but essentially, let's say we wanted to get the difference of like these two locations. This would basically mean now, instead of being a substring that ends at character 5, this is saying we want the difference between a string with 8 characters and a string with 5 characters. So a string with 5 characters goes between 0 and 4, and a string with 8 characters goes between 0 and 7. So we need the difference between these two. So really what we're asking for is like, give us the sum of 5 characters at locations 5, 6, and 7. And so if we look here, this should be -2, right? Or sorry, this should be -1, and that's in fact what we'll get. We'll do -2 minus -1, so we'll get -1. So a little bit confusing. You can also draw a normal prefix sum and just add this on at the very end once we do this, if this is a little hard to understand. But now, essentially, once we have this, we need to figure out where the locations are, like where the substrings are that actually have a matching number of vowels and consonants. So what we're going to do is we're going to handle this case first, so we can write that down. So we want to look for locations where number of vowels equals number of consonants. And the way to do this, I think this is actually like a LeetCode medium problem. I think it's like subarray sum minus k or something. Basically, anytime you have the same number multiple times in this prefix sum, like let's say we have a 0 here and a 0 here, that means that there is some subsection here that has a sum of 0, right? To go from 0 to 0, that means like this subarray here has a sum of 0. And we can look, in fact, and they do, right? So let's take a look at what this means. So here we have this is the last part. This is a string of length 0, and here we have a string of length 2. That means that the string of length 2 minus an empty one has a length 0, and this does indeed have 0, right? So obviously anything with 0 will have, like the entire thing, will have a length 0, but also we can look at this for other numbers. So let's take a look at this for other numbers, like for example 1, or like -1. So anytime we reach -1 multiple times, if you think about it, in order to get -1 multiple times, we had to do some operations, like, right? We had to do some adds and subtracts. So like, let's say from -1, we would subtract like 2, and then we would add 2 again. That means in that region where we subtracted 2 and added 2, that region sums up to 0. So like this region sums up to 0, this region sums up to 0, and so on, right? So anytime you have a repeating number, that means you have a subarray where the number of vowels equals consonants. So we can look at another example here, for example. So we're saying here that this is a substring of length 3. So this contains characters 0 to 2. This is a substring of length 5. So this contains characters 0 to 4. So the difference here should have a subarray sum of 0. So that's going to be characters 3 and 4. So if we look at characters 3 and 4, that does indeed have a subarray sum equal to 0. And let's do one more. So these two are also -1. So let's take a look at this whole region. So this is a subarray of length 3. So characters 0 to 2. This is a subarray of length 9. So characters 0 to 8. The difference here is characters 3 to 8. So characters 3 to 8 should have a subarray sum of 0. So let's take a look. And indeed, we do have 3 -1s and 3 positive ones. So basically, anytime you hit a number, if we were just asked to count for like how many total substrings are there that have this, anytime we hit a number, we can just check, okay, well, how many times, like we can just have a dictionary of the actual prefix total and the count. So here, for example, we hit a 0, we'd say there are none, so we'd make 0 equal 1. Then this would be 1 equal 1. Here we're going to say, okay, well, we have a 0 before. So because we have a 0 before, that subarray from the old 0 to this 0 has to be some 0. And if we had a bunch of zeros before, then all of those would be 0. So for example, for this 0, this is going to be a subarray, this is going to be a subarray, this is going to be a subarray. So it's pretty easy to do, and this is literally that subarray sum minus k. I'll link that problem actually, because that one you would want to understand before doing this. But essentially, the code would look something like have a hash map of prefix, total, and count. And then as we go through the totals, if the total is in here, then add count to result, right? So we'll have some result, and then also at the end, also increment count of the total. So it'd basically be, like that's pretty much it, right? So we would just go through it. We'd say like, is this value in our hash map? If it is, then let's increment our result by whatever that value is. And let's also increment the count in the hash map by 1 after we're done with that. So this is how we could do it. But the problem with this is we also need another condition. Like this is fine. We could do this in O of n time. But we also need this condition here. So this vowels times consonants mod k equals 0. And this is going to be like the tough part of the problem. So let's write that down. So vowels times consonants mod k equals 0. This is the hard part because this is basically saying like we have to figure this out somehow. So let's actually simplify this as well. So if we only check areas where the number of vowels equals consonants, and we can do this with this prefix something, right? Like anytime, like for example, let's say we hit this 0, we can be like, okay, let's look for the locations of our other zeros, and then we could figure out what the subarray is, right? So like this would be a subarray, this would be a subarray, and so on. So what's the length of this thing, right? If we know that vowels equals consonants, and we already know we can just check only valid locations, that means we know if vowels equals consonants, we can replace consonants with vowels, right? And how many vowels are there in a string of length L? Like let's say we calculate an index here, so let's call this index j, and let's call this index I, so this would be like a string of length 4, and that is correct, right? So we have a string of length 4, and it does have the same number of vowels and consonants. So the length, we can write this down as well. So the length equals j minus I. But how many vowels? Like what is the length? How do we write the length as a factor of vowels? So length, if we think about it, if vowels equals consonants, it's basically going to be 2 times vowels, right? Because if vowels equals consonants, then the length of the string is just 2 times the vowels. So we can factor this out. So we could say vowels equals length over 2. And now let's replace this equation. So we're going to say length over 2 squared mod k equals 0. And what is the length? So the length is just 2 indices, right? So length is just j minus I squared. Oh, and by the way, yeah. So let's also factor out this 2, right? So this 2 is just going to be like this, right? Because length over 2 squared is just going to be like this. This mod k equals 0. And the problem is here, what we really need to do, kind of like in the prefix sum, notice that whenever we're at an index j, we can just figure out the count of something else, right? So we kind of need to do this. In order to do this in n time, we can't have the I and the j in the same part of the equation. We have to have one be something else that we can look up. So like if we have I saved, and then we can go through j and look up where I is, that'll be fine. But if they're on the same side of the equation, like we can't calculate both. We can't have an n squared solution. So what we really need to do is figure out a way to get this to be separate. And the way to do this is if there's some kind of way to get rid of this, right? Because if we could get rid of this square, then if we had like j minus I over 4 or something, mod k equals 0, then we could easily like move stuff to the other side and figure this out, right? Like, that's totally fine. And then we would have j as a factor of I, and then this would be doable. So the way to do this, and this is honestly the hard part of this problem, is we need to find a way to get rid of this square. And that's why I said these algorithms are kind of hard, because there is some math involved. So if you think about it, let's just get rid of this. Let's just get rid of this 4 altogether, like this squared, and let's come back to that. So let's say we have the length squared equals, or mod k equals 0. So what we really need to do here is we need to figure out what the length needs to equal to get rid of the square. And the way to do this, and like I said, this is very tricky, is you have to do the prime factorization of k. And so let's look what that would look like, basically. So the prime factorization is essentially, if you don't know what that means, it's all of the prime factors that multiply out to be k. So if we have a number like 15, this would be like 3 and 5. If we have a number like 60, you can just take big numbers and keep making them smaller. So 60 would be like 20 times 3. 3 is prime already. 20 would be like 10 times 2. And then 10 would be 5 and 2, right? So you basically get like 2 squared, 3, and 5 would be our factors. So that's what we need to do. We need to get our number, k, and get divide it into prime factors. And there's a way to do that. Like, there's just an algorithm you can run to make prime factors here. So then we would get something like prime factor 1 to some power plus prime factor 2 to some power. These are all going to be different. So I'm just writing x, but they're not really going to be x. They're going to be like some different power. So maybe it's like x1, x2, and so on, right? We get all our prime factors to some power, right? Because the prime factor can be used multiple times. For example, 8 is like 2 cubed. So here you get 2 cubed and so on. So when you get the prime factorization, if you're saying L squared mod k equals 0, that means, what this means is L is a multiple of k, right? So L, in order for L squared, or I guess in order of L squared, not L is a multiple of k, but L squared is a multiple of k. So this is going to be L squared, right? Because in order for this to be 0, that means L squared has to be k times something, right? K times 1, k times 2, whatever. Like, let's say k is 5. In order for this to be true, then L squared has to be like a multiple of 5 in order for this to be true. So if L squared is a multiple of k, and we have our prime factors, then what does L have to be? And also, think about it in the prime factors. So if L squared is a multiple of k, that means L squared has to contain all these factors. So for example, let's say k is like 15, and the prime factors are 3 to the 1 plus 5 to the 1, or times. They'd all be times, right? But yeah. So like, these would be all the factors, and these should also be times as well. So we can get rid of these. So this is going to be like times and times. That means that L squared has to contain at least 1, 3, and 1, 5 to be a multiple of 5, right? So whatever our number prime factors into, L squared has to contain all of these values at least, and then it can have something else, and that would make it a factor. So if we actually do the square root, if L squared has to contain, you know, like let's say L squared has to contain like 3 P1s, 3 P2s, 2 P3s, and so on, just making some random number, right? So let's say these are the prime factors. Like, whatever this prime factor 1, k has 3 of them. Whatever the second one is, k has 3 of them. Whatever the other one is, this is this. So if that's the case, then L has to have 3 over 2 P1s, 3 over 2 P2s, and 2 over 2 P1s, or P3s. And this also has to be rounded up. So in this case, it would be 2. In this case, it would be 2. In this case, it would be 1. And that's because if L does have indeed 2 P1s, 2 P2s, and 1 P3, right, and they're all multiplied by each other, when you do L squared, you're going to take this and you're going to square it. So then you will have 4 P1s, 4 P2s, and 2 P3s, right? And this is enough. But if you round it down, then these would be 1, 1, like this, right? And then when you square it would be like this. And then when you square them, you'd only have 2, 2, and 2. And so this is like really the hard part of understanding. Just make sure you understand that like when your k is divided into some factors, when you get the factors for k, in order for something to be a multiple of k, that number has to have at least these factors. And so if that number squared is these factors, that means the square root of that number has to have all of these factors divided by 2, but you have to round up, right? Because if you need 3 and each one has 2, then it would work. But if you need 3 and each one has 1, then it wouldn't work. So now we know that for L, the prime factors that it needs are these factors here, right? Whatever they were before, divided by 2, rounded up. So we can say that L mod k, this new k value that we have here, right? This new k value, if L squared mod k equals 0, that means L has to at least have these factors. So we can call this k new. And so what would happen here is basically we can calculate what k new has to be, right? So let's do some examples here just to really get this to make this easier to understand. So let's just try like our old k is 120. So let's get the prime factors of 120. So it would be like 60 times 2. And then 60 we can break down into like 15 times 4. And then 15 we can break down into 3 and 5. And then this would be 2 and 2. So these are the prime factors of 120, right? So we can write this down into, we need 3 2s, or we can write like 2 cubed times 3 to the 1 times 5 to the 1. And L squared has to have at least this. So in order, what does L have to have? L has to have at least 2 squared, right? Because half rounded up. And then it has to have 3 and a 5. So L has to have these numbers at least, which means that this k new has to be this value. So if k new here is, this is 15 times 4, right? This is 60, I believe. So 60. So L has to be mod 60. And then L squared would be mod 120. So hopefully that makes sense. And let me just make sure I calculate this correctly. I think I did 15. Yeah. So k new has to be 60, right? And now that we have k new, now it's going to be pretty easy. So now we have another equation. So remember the length of L was just j minus I, right? Where it's like our last index in this prefix sum. So if we go back up, it's just our last index in the prefix sum minus the first index. Like that's the length of the string, right? So it'd be like 5 minus 1 and so on. So now, if we have that, this is totally doable now. So now we have j minus I. We can actually just do it like this. So j minus I equals k new that we calculated with the prime factorization. And now, or actually not quite like this. So j minus I mod k new, I'll just call this kn equals 0. And now this is actually doable, right? Because if we do this, that means that we can actually, so in order for this to be true, that means that j mod k new minus, or yeah, like this, I mod k new has to equal 0, because this is just like a basic mod property. For example, let's say k new is like 5. In order for a difference of 2 numbers to be 0, so let's say this is like, let's say I is like 7. In order for this to be true, this would have to be a number like 9 or something, I believe would work. Actually, would 9 work? No, 9 wouldn't work. So this is 2. So you'd have to get a number that, because 7 mod 5 equals 2, you'd have to get a number that's bigger than 7, and that mod 5 is also 2. So a number like 12 would work, right? So we can get 12 minus 7, and then this mod 5 equals 2. Or equals 0, sorry. Yeah. So this is kind of the same thing here, right? You can separate it out. So if this is the case, that means that j mod k new has to equal I mod k new. And so if that's the case, if j mod k new has to equal I mod k new, and we are able to do this other part, right? We're able to do this part in O of 1. Now we can also do this part in O of 1, because instead of for every single value just storing the prefix, we're going to store two things in our counter. So we're going to store prefix, and instead of storing the count, or we are going to store a count, but we're going to store a tuple of prefix and I mod k new. Then when we're at a j, we can just check, is the prefix in here? And is j mod k new in here? And if it is, give me that count, and that's how many beautiful strings I have. So this is definitely super confusing. I understand. It's like, that's why I said this is kind of like math. The main thing you have to realize is this prime factorization thing, where if a number is divisible by all these digits, that means that the square root of a number has to have at least half of all these digits rounded up. Once you get that, and once you get, like, I would suggest you can also just try like a basic prime factorization of a number, and that would help you a lot. So anyway, once we get this, we can use our prefix sum array, and we can just calculate I mod k new. So instead of storing I, we'll just store a tuple of I mod k new and our prefix, and then we can check for that in our counter. So yeah, that would be pretty straightforward. Like, we're just going to go through our indices. So for example, for index 0, we'll say like, okay, well, what is that mod k new? That's just 0, and so on. And then for this, like, let's say k new is like 5, we would store something like 0 for the I mod k new, and then we'd store 0 for the value. Then this would be 1, and then 1 for the value, and so on. And then once you get the 6, you would get 1 again, and so on, right? Because you're basically doing this, I mod 5, and so on. So those are the two parts. We have to calculate this k new, and then we have to also, so we don't actually need the prefix sum. It's just easier to show. We don't actually need to do it because we're basically going to iterate left to right. So we can just maintain a sum. We never need to really get a range, but it's easier to show it this way. So those are the two things we need. We need the total sum, and then we also need the k new to figure out exactly where this occurred. And the difference between I and j has to be that. So now we have enough to code it up. And I know that's why I'm kind of like hesitant to make videos on these things, because they're very complicated. So I think this is like a LeetCode very hard. So let me know what you guys think afterwards, but let's code it up. So what we first need to do, oh yeah, there's one more thing that I forgot, actually. So remember, our thing originally was L squared, but then it was L over 2 squared, right? Because it was the number of vowels. So the number of vowels is the length over 2. So we actually had L over 2 squared, which means if you factor this out, we have L squared over 4 equals K. And so that would mean that if L is some K new, it would actually be L over 4 mod K new, right? And so if you were to do the square root, you would also do the square root of this 4, actually. So it would be more like this. So it would be L squared over 2, actually, right? Because L squared over 4 is K. If you did the square root here, this would be 2. So if L over 2 is mod K new, that means you have to take the K new and multiply by 2. Because, like, let's just try some value. Let's say L is, what value could we have here, I guess, that would fail otherwise? I think we can do like 9 and 3 would work. Yeah. So let's say L is 9, K new is 3. So this would indeed be 0, right? But the problem is you also have to divide the 9 by 2. And so now we'd have like 4.5. So really what you need to do is you need to do 9 mod 3 times 2. So whatever the K new is, we're going to also multiply it by 2 because there's this extra 4 factor here that turns into a 2. So we're going to move the 2 over here. And so whatever the new K new is, we're going to make it multiply by 2. And now that should be actually everything we need. Okay, so we're gonna start with k new equals 2 because we always need that extra 2. And then now we're essentially going to do the prime factorization for the rest of the numbers in k. So we're just going to say for I in range. And k is also kind of small, so you can do like a brute force. You can do a brute force prime factorization. There are more effective ways to do it, but they're not necessary for this problem because this is such a small part of it. So, and this is already a super long video to begin with. So essentially what we're going to do is we're going to do something like this. So k can be 1 to 1,000. So we're just going to say if k is less than I, we can break because obviously k can't divide into that number, right? So if k was like 1 and we were on number 5, then 5 can't be a factor and 6 can't be a factor and any of those can't be a factor, right? If k is smaller than I, it can't be a factor. So what we're going to do is we're actually going to take a factor count. So we're going to say factor equals 0. This will be the count of that factor. So for example, this will be the count of 2's. Then we'll say while k mod I equals 0, meaning while we can divide k by I, let's divide it by I. And then let's add 1 to the factor. So for example, if k was like 8 and we were on factor 2, we'd say, okay, let's divide 8 by 2. We'd get 4. And now we have 1 factor. Then we can divide that again by 2. We'd get 2. Now we have 2 factors. And let's divide it again by 2. And we'd get 1. So we have 3 factors. So while we can divide it by this number, let's keep doing it. And that also gets rid of the issue of dividing by bigger numbers. So you don't have to worry about like using non-prime factors because like let's say 4 is non-prime. You will just divide 4 by every single factor of you will divide your number by every single factor of 4 as much as you can already, so you'll never be able to divide it by 4. So if you wanted to optimize, you could do something else, but like I said, this will be fine too. Okay, so now we have the count of that factor. So we're going to say if factor, if it's a non-zero count, then we're going to take k new and we're going to multiply it by that factor and the number of counts. So let's say we had like 3 2's in k, so we'd need to take k new and multiply it by, remember, if we had 3 2's, we would need the upper bound of dividing it by 2. So that's what we're going to do. So we're going to say k new times equals I, right, whatever the factor is, to the power of ceiling factor over 2. So if we had like 3 2's, then we would divide it by 2, we'd get 1.5 round up, so we'd say we need 2 2's. And that would be that, right? It would be 2 squared, and so on. So we're essentially taking every factor of k, dividing it by 2, and then multiplying k new by that. So now we're going to have this dictionary of counts, and the count, remember, is going to have the prefix, or the sum at the index, and it will also have the index mod k new. So we're going to say counts equals default dict int and counts of. So the other thing, this is why I made this prefix sum, because you need to make sure, the reason I added this is because you need to make sure that the sum of the empty array is 0. Because then you can, if you see a 0 again, this is a range that's valid, right? Because you need to take into account the total array, right? So this means an array of 0 letters and an array of 4 letters. So if we take a look at the first 4 letters here, 0 through 3, they do indeed have a sum of 0. So this is also in that problem that I'll link, where you have to do this part or else it'll fail. You have to make sure that you can actually get a prefix sum of a completely empty substring. So that's why I was doing that. So I made it a little bit more confusing. So essentially that's going to be our default value. So we're saying, okay, let's say the count of the completely empty array, the total is going to be 0, right? Because an empty string should have a total of 0. And I mod k new there is going to be 0 because 0 mod anything is 0. So we'll add 1 here. We'll have a result. And then we'll have our val set of a, e, I, o, u. And we're just going to maintain a sum variable. We don't need to do the prefix sum because we're just doing a one pass left to right. So we'll say value here. We can't use sum, so we'll use value, and then we'll say basically for j in range 1 length s plus 1. And the reason we need to do that is because if we go back to our prefix sum picture, right, j is going to represent the length of the actual string, not the index. So this is like length 1, length 2, length 3, and so on, right? So that's why this needs to be length n plus 1, because we do also need to have where j is the length of the string. Okay. And then value, we're going to add the character here. So we'll add 1 if s. So if this is a length 1, if j is 1, that means the index we need to add is that index 0 of the word, right? Because if j is a 1-letter word, that 1 letter is at index 0. So we need to look at sj minus 1. So if it's a val, we'll do this, right? So if sj minus 1 is in vowels, we'll add 1. Otherwise, let's add -1. So now that we have our value, now we need to count up, have we seen this before? Right, and this is basically the crux of the problem, and we can do this in one time. So we're going to say, let's take whatever the value is, and whatever the j is, mod k new, and if we've seen this before, then we will add that count. Because this is the part where we do it here, right? So whenever we pass it the first time, we will increment it by 1. So counts val j mod k new plus equals 1. So what that would look like essentially is like just doing like a small run of it. We'd say like, okay, here our counts of 0, 0 is 1. And let's say our k new is like 5 in this case. Then here are counts of 1. And then 1 mod 5 is 1 is 1. And then here we're going to say, okay, well, have we been here before? And so even though this subsection is technically the same, we have to also figure out, like, is the k new part true, right? So this index would be 2 mod 5, so this is 2. So we don't actually have 0, 2. And that's why it's important, because if we go back, so technically, yes, a string of length 2 does have the same vowels as consonants, but if k was 5 here, this would only be length 2, so it wouldn't work. And that's why you need the k new. Okay, so essentially we just increment by the old count, and then we update our count here, and finally we return results. So there's not that much code, but it's very hard to understand it, and I definitely, if you have any questions, also write in the comments. I'm happy to clarify things. It's pretty hard to explain this one with the prime factorization exactly how it works. So we can run it. You can see that it should be fine. Yeah. So we can talk about the complexity here. So essentially, our non-optimized prime factorization is basically going to run whatever. So we did just hard code a value because k, like I said, k is relatively small compared to anything else. So this will run like 1,000 or something, which is like pretty small. You can make this more efficient, but this is fine for this problem. And so yeah, this is going to be like, let's just hard code a value here. It's going to run 1,000. I guess it's a constant, so we can actually get rid of it. And then for every single time, we will basically divide it by the factor. So it's going to be like, really what it should be is like 1,000 log, and then the actual bit that you manipulate it by. Or not the bit that you manipulate it by, but the number you divide it by. So if you had a number like 6 and you divided it by 2 a bunch, it would be like log k, really, or something like that. So maybe we can write like k log k or something. But yeah, this is basically pretty small because k is only 1,000 compared to the other stuff. And then the other part is we're essentially doing a one pass here. So because we're doing a one pass, this is basically O of n. And yeah, like I said, this is pretty much inconsequential because you can say this is only 1,000 or so on. And for the space, so we didn't make a new k new. We didn't really need anything for that. But we do have this default dict of counts. And so how many unique values can you have there? I think it's something like, well, actually, it doesn't really matter. It doesn't really matter how many unique values you can have because the most unique values you can actually have is only O of n because we're only going through our array once, right? So even though you might be able to have like n times k or something or k new unique values, you're never going to get that many because you're only going through your array one time. So for every single index, you'll generate a value and they might all be unique. So it's going to be O of n space. So yeah, hopefully you like this one. Definitely kind of a long one. And definitely if you have any questions, write in the comments. And I will see if I'm going to do the other problems in the bi-weekly contest. I think honestly it's even harder than this one. So I might just not do it because I don't want to make like super long videos that are super confusing. So yeah, hopefully this was helpful. And if you did like the video, please like it and please subscribe to the channel. And I'll see you in the next one. Thanks for watching.